and welcome everyone. Thank you for joining us. I'm Scott Dybwad. I'm a lawyer and patent agent with Borden, Ladner, Gervais. We're a full service law firm with offices throughout Canada, and I'm based with the intellectual property group out of our Ottawa office, pardon me. I also sit on the editorial board for DeadCat LiveCat, a quantum computing focused collaboration of IP lawyers with Zuber Lawler in the US, Marks and Clerk in the UK, Schindler's in South Africa, and of course, BLG in Canada. And I'm very excited to have joining me today Wojtek Burkot. He's the co-founder and chief physics officer of BEIT, a quantum computing startup based out of Poland. And on that note, welcome Wojtek. Great to have you here today and joining me here at this conversation.
Thank you very much for having me. Just a small correction. We are formally incorporated in Delaware, like every other startup, right?
Of course.
And we do have an R&D office in Poland, Krakow, Poland, but also one in Toronto, Canada.
So very good.
And we have just hired our first employee there. Luckily, the second physicist. That was the hardest hire for us to get enough physicists there. So indeed, I'm Wojtek Burkot. I'm co-founder of BEIT, together with my business partner for over 20 years, Paulina Mazurek, our CEO. We met a long time ago at Motorola, then continued through Google, Allegro, and we co-founded BEIT when we thought it's a ripe time for the quantum computing hardware to actually deliver on the promise within my lifetime. I'm pretty old, so that's important.
Well, I mean, you've had a really interesting journey, Wojtek. I mean, you started as a physicist, pardon me. You went to Motorola, then to Google, then to Allegro, and now you found that it was the right time to sort of jump into the quantum space. So tell us a bit about that. What inspired that move? What made you think it was the right time?
Well, I don't think I made actually a real move. Since my physicist times, I was always interested actually when at the university I lectured on this. What are the physics paradigms for computation? What's computable, what's not? Why? Why do we use computers to model mathematical abstractions? And that was my core interest forever, throughout my career, regardless of who was paying for bread and butter. And especially the tipping point was my strange visit. Poland was still a communist country. And I got invited by people from MIT, the names famous in the quantum space, Professor Tommaso Toffoli, Toffoli Gate, and Professor Norman Margolis, Margolis Gate. And they were coming from the LCS at MIT, and we were working on some other physics motivated paradigm for computation, yet they were already starting under Professor Richard Feynman with quantum computing. I missed Feynman, but the Toffoli and Margolis made a lasting impression on me. And ever since that visit, whoever was paying for bread and butter, I was doing quantum computing, right? In my free time, on and off, along the same lines. And why the switch to the startup? Because we thought that the hardware is about to be ready. And also because of that past of like 30 years focusing on this, I didn't feel really comfortable sharing everything I had with Google. By American job contract, everything I was working on in my private time belonged to Google. So I didn't think it was fair. And that's why I quit Google. And then that's why we started BEIT with the really noble adversary, the third co-founder, mathematician, who was just a designated refuter of the crazy physicist ideas, right? With his formal approach to problems and ability to formally prove them in the language I could understand. So some of those ideas were just shut down initially, but once he was having difficulties shutting down some of those and coming up with his own, we decided it's a time because the hardware might be ready in our lifetimes.
And
so,
yep, go ahead.
One more thing, you know, this is more about me now. I missed the mobile revolution while working at Motorola on it, right? We were delivering 3G networks globally. And I didn't think it was anything big. Then I essentially underestimated the internet revolution, despite being exposed to the early stages of the web browser at CERN when I was still a physicist. And I thought it was like, come on, I just fixed an important problem in the CERN library, and those guys are doing just the documentation system. So René Brien, the head of the CERN data division at that moment, he introduced me to his team. I was like, nah, it's unimportant, right? So that's how I missed 2 revolutions of my lifetime. And I was adamant that I will not let the QC revolution to pass by. So that was the real motivation of starting this now.
The third time's the charm, as they say.
Yeah, the third time is a charm.
I understand that BEIT is software focused and hardware agnostic, but you've mentioned that the hardware was finally kind of getting to the right place where you felt it was sort of time to jump in. So what was happening at that time with hardware that's now that, allowed you to see sort of a maturation in the hardware technology that you felt made it the right time to kind of jump in?
Right. So I had big doubts about some of the hardware solutions touted as the quantum computers, and I will not mention the names out of kindness. Actually, they get to that idea too, and switching tags. Let me talk about the NMR computers, right? There is no entanglement. This is pseudo, pure state, what is there, so it cannot provide the advantage. So it's useless as a better computer. We need a better mousetrap for some of the problems which we are facing. And if something doesn't offer that, it's of no interest, even if it is driven in a sense by the quantum mechanics, right? If you think about like the floating gate field effect transistor works, it's a quantum device, right? The current is so small that you are struggling to overcome quantum effects in such a transistor. And why don't we use them rather than fight against them to get some speed up, which was luckily proven possible early on. Theoretical works by Shor and Grover essentially showed us that there is a way. And this was initially, this was a crazy idea, and the rather stupid, if I might say this. If you draw the line provided by the Moore's law and then derivatives, I know it's about something completely different, the optimal size of the chip on the die of a given size and at the given rate of errors. But essentially, people draw many conclusions and say how the technology is progressing. So all those lines get to an interesting point sometime in 2023. So we are switching by a single electron. You have a size of the transistor comparable to the size of an atom, or the bigger ion if you just blow it up by reducing of some of its electrons. And then essentially building one of those costs about the GDP of the global GDP of the whole Earth, right? So this is obviously, they are pointing to a singularity sometime in 2023, and that was initial motivation. But then we realized that there was a breakthrough, I think, when I learned about the Google approach to quantum computing. Harmut Neven asked me to go to the execs. I was an old hand, so I could go to Alan Eustace and actually ask for the funding for this thing. But then I realized it might be getting serious. Google is really serious about technology. So once they started it, with all the attacks they did initially with the really bad ideas, but some extremely good, especially one with incorporating the group from Santa Barbara into Google to develop their machine. So that was a great idea. But then I realized that it's happening, right? And that motivated the timing as much as this funny thing about the singularity in 2023. So that's more or less what motivated us to start at this moment. And then there were pivots, and we'll get to that why it mattered, because demonstrating something at like 2 5 qubits is completely different thing of providing this advantage, which I mentioned, which is extremely important for me. There is no use for the quantum computer, which is weaker than the HPCs of today. So that's something which made us pivot several times along this journey.
Well, let's maybe talk a bit more about those pivots then. So, you know, you had this initial vision and then you're coming to certain realizations along the way. So how has BEIT changed course over the last, I guess it's been about 4 or 5 years now since its founding? Like, can you maybe tell us a bit about how you've changed your...
2017, yeah, so the changes, right? First thing, you know, being a small startup, essentially from Poland, as you mentioned, required us to prove our worth, right? In that space, people were expecting physics PhDs. We had one physicist with PhD and one mathematician with PhD. And then we thought that we'll be doing good with just a bunch of the really talented individuals, regardless of their academic credentials. This is not very convincing for people who are bound on hiring physics PhDs, even if those cannot really program and cannot really think in terms of the complex systems being solved numerically on any hardware. So we did a change here. And then we wanted to establish our name in what we are doing, which was kind of tricky until you were able to show that you have something other people don't, right? So people that something which was very closely linked to my ideas from the past related to the Groover search. And you know, there was a nice moment, I'm doing the fast forward now, when we got a review of our paper in PhysRefe. One of the reviewers said, well, this is for the first time since 2009 when anybody was able to prove the scaling and the optimality of the new quantum algorithm. And it's like, wow, indeed. And that's something when you are not running a department at the university, but a small startup with youngsters who are just working on their masters. That's really something, getting this approved and actually making sure that those ideas were not only theoretically interesting, but we can make them run on the actual hardware. That was really something, because then you do something which in math would be 2 steps of the induction proof. So here is a very small version of that stuff, and it runs for real. Like, you know, people say that to do 6-qubit Groover search, which is useless. It's like searching for the spent match in the matchbox full of matches, right? Because of the sizes involved. Nevertheless, that's the limit of the hardware capability, provided you use our software, our method of solving that problem. Nobody else could do this because it takes something like 1,000 2-qubit gates, which is out of bounds for any of the existing NISQ hardware, right? If you do our stuff, then you can reduce that and bring essentially the point where those things will be useful forward by something like 2 to 3 years, because it's a factor of 10, and that's something which happens in that industry in about 2 to 3 years. So that was the first moment when we realized that we can do something better than anybody else. And this still holds, right? There's a benchmark on the Groover search. You'll see that it requires about 1,000 CX gates. We did that in 23, right? Not exactly the same thing, but still better than the classical solution, which is important. And then besides this proof on the existing hardware, you are formally proving the scaling, saying that if it works for 6, it will work for 6,000. And that's what we did. And that's the power of what we are doing, protecting the IP. And I think we'll get to that because it's also very important for us. So that was the first thing, right? Making sure, and you know, this also touches on our hiring strategy build. It wasn't accidental, haphazard. It was just designed that way. So having those guys and being able to come up with those solutions and being able to partner on the basis of those solutions with the best hardware manufacturers, you know, those conversations are strikingly similar with those guys. So it's like, nah, we know better. All right, can you do this? No, nobody can. Well, run our stuff. Oh, it works. can we partner, right? And there are many things around this, but that was how we established our position in that industry. Some other methods were also employed. You know about our results in the quantum challenges. We essentially stopped participating in them. We did what we wanted there, and that's enough. We have a pipeline of candidates which we are satisfied with, and we are extremely selective. This just works as a design process with the expected outcome and measurable along the way. So that was our first pivot. We are not expecting, for the reason that our unstructured search will be something extremely important in the far future. It's not giving enough of the power advantage over the HPC for that to matter. But that was letting us work with other guys who needed that kind of proof to establish that their hardware actually works. And it helped us to establish our position in the industry. So that was the first step. And we are equally comfortable with generating the ideas, pushing the manufacturers like, hey, provide the mid-circuit measurement. This is something which we believe can benefit the computation despite what the textbooks say. But by the way, anybody not doing this is kind of missing the boat. You cannot do the fault tolerance. You cannot do the error correction. You cannot measure and feed forward the measurement result to the subsequent computation. So why bother if it will be just a toy? So that was something which we were stressing from the first moment. And we got a partner understanding this, right? Between first and second set of our runs, Honeywell provided mid-circuit measurement, and we showed that it's actually beneficial. And we before that, we protected part of that with the appropriate patents. So we are essentially saving resources by doing it our way. So that was the second tack. And the third one, I'm kind of again jumping forward a bit, was realization. And again, it was serendipitous. So we met people who are at completely different stage. And I'll use what they say, and then you might know who I'm talking about. But essentially, we are, for the quantum computing, we are in for the moonshot, right? And getting to the moon, like all the NISQ machine, regardless of the underlying physics and the brand of the provider, all those essentially are trying to build a ladder to the moon one step at the time. Well, everybody knows you need a rocket engine. And there are people, luckily, there are people who are building those rocket engines, right? Meaningful tolerance. And that's our most recent pivot. We did re-examine all our previous patent applications. About half of them pertains to the fault-tolerant machines because it saves the critical resource there. We were optimizing for the 2-qubit gates because that's the limitation on the existing NISQ machines. And then we moved to optimizing for small rotations like the T gates. Half of our patents for NISQ are usable in the fault-tolerant model. And obviously, I think I thought about this as an answer to some of your other questions, so we might get there. But essentially, that's also the difference, and that's the pivot, yet another pivot we made. So now we are like committed to fault tolerance, and we treat the remaining stuff as the ability to talk to people, show what we can do, and fight some hype. If we'll get to that, I guess, as well. But that's something which we are really focusing on right now. On the way, we started working with D-Wave initially as a part of the CDL accelerator. And as such, we generated several patents for the quantum-inspired technologies. So massively parallel annealers like D-Wave, like Fujitsu DAO, and then trying other architectures, whether they can run this. You can go to our website and you'll see the emulator of D-Wave, the completely classical one. And we try to employ the techniques in there for some of the parallel architectures like the Cerebras CT2. We are talking with those guys. We are after first test. We were talking to Fujitsu on their DAO machines, and our own stuff runs either on the CPU or on the GPUs as we want. So, but this is straight, and so are some of our patents for the NISQ specific machines, because in reality, if there is a quantum advantage in the future, it will not come from the NISQ machines, it will come from the fault tolerance system.
Can you tell us a bit about how patents are perhaps helping draw investment or growing BEIT and positioning yourself for your moonshot?
All right. So actually, I think that's easy, but this is less of the focus with the VCs. They do realize that the revenue from patents comes late, right? The timeline for this is pretty long. It's extremely valuable, especially the European patents are more valuable than the American ones, German ones, for example. But the timeline is long. And luckily, the timeline for the quantum computing hardware is similarly long. So we made that connection, and we think that we have that kind of time. So it's less for the investment community. If somebody understands that and buys this, that's perfect, right? That makes the conversation easier. But we are really driving for the real impact. If you need our patented software to bring the quantum revolution forward by, if we are going, the estimation is by the NISQ trajectory. So that would be 10 years, right? Now we know that the hardware will be sooner, but the fault tolerant hardware will be sooner. But judging by the improvements, the trajectory of the NISQ machines, with our 100-fold improvements, we are bringing the quantum revolution 10 years earlier. That's the, hand waving kind of the argument. We have proven, well, we did our unstructured search in 2019. Nobody have beaten our result till today. So it's like those 2-3 years seems reasonable. Nobody was able to match what we did with our patented software. So we are aiming this at the real benefit rather than just for the investment needs, which again makes it harder. But in the long run, I do think that the eventually people selling snake oil will get routed out of business for the reason. It might take some time, and we will be there. We will definitely be there with the investment, or without it. We'll prefer with, because then it will be bigger and more important. And we want to be in certain layers of the QC stack, because it brings the revolution forward, and also it lets you handle larger problems. And again, jumping ahead, a lot of the industry is working at suboptimal solutions because there is no computing power able to find the optimal solution for the problems they are facing. So that's where we want to make money, and we are patient. We can do that in a couple of years. It'll be great to survive till then, preferably on the investment.
So Wojtek, if we're now 2-3 years into the future from now and having this conversation again, what do you think the likelihood is that BEIT will be making or have made another pivot?
Well, I think there are no more pivots which I can imagine needed forward, right? If the fault tolerant systems are what we need, right? If when I was talking to those guys previously, and they were asking whether I need fault tolerant system, I was like, no, I just need to be able to run a circuit of 200 qubits for something like 2,000 2-qubit gates. And if you provide me with that, I'm happy. But then if you do the calculation, it shows that, well, essentially you are in fault tolerant regime if you provide those parameters, right? So I was avoiding the answer, but those guys are providing the answer in the sense that they might be a hardware which does exactly what we need there. And then that would be the focus. So we think that we selected the layers in the quantum software stack we want to operate for the reason we want to stay there. And I don't think that we need to pivot much from out of this. That was actually the same layers we were working on when we were thinking NISQ. we claim that we do hardware agnostic algorithms and the hardware aware implementation. So we are just changing the implementation, also optimizing our circuits for something else. It used to be 2-qubit gates because that's what limiting NISC. And now it is the number of T gates or small rotations because that's what's limiting the fault tolerant architecture. So not much of the pivot at the ideological level, but yes, it is a pivot if you think that you are now optimizing for something else. But for the people we have, is you're right. The cost function is different. That's all it changed. So it's not really a pivot at that level.
And finally, Wojtek, we'll just kind of pivot to the end here. It's becoming a bit of a tradition in our interviews here at DeadCat LiveCat to finish on a softer tone. And we were wondering if you could maybe tell us if you could invite any 3 people from history to a dinner party to discuss quantum computing, who would you invite and why?
Well, I missing Feynman at MIT, so obviously he'll be the one of those. I missed him by a couple of years, but his students made a lasting impression on me, and actually they directed what I've been doing since since 1993. So Feynman for sure, and 2 other geniuses. Turing, very clearly, he had everything. There was already quantum mechanics when he was having his thoughts, right? So knowing that it can be done, I would love to pick his brains on the potential of the quantum computing compared to the Turing machine, which is essentially an abstract model for the classical computing. And the third one would be, I have a difficulty here, like the tie for the third position. It will be either von Neumann or his close collaborator Stanisław Ulam. The Polish guy, pretty shy, so you will not see his name, especially that some of their works are still confidential. But those guys knew a thing or two about efficient computing, and the von Neumann automata and the stuff, you cannot really tell whether this was von Neumann or Ulam. They were both working on that. From other sources, it is clear that von Neumann was a genius, right? So one of those guys would be the third one to have that dinner with and talk quantum computing.
Well, that would certainly be a very interesting discussion with that collection of people, and obviously a lot of impact on the kind of work and research and developments you're doing today. So Wojtek, I just thank you again for your time today. We've really enjoyed the conversation here and learning more about BEIT and getting your deep insights into what's going on at BEIT and in the quantum computing community at large. So thank you again for your time. It was our pleasure to host this interview and have this conversation.
Thank you very much again for having me and listening to my ramblings on the quantum computing and the technology in general. Thanks a lot.